So I'll be presenting on behalf of both of us, and our project is for K-Health. Someone once told me every presentation should start with a joke. So a SQL query walks into a bar, it sees two tables, so it asks, can I join you? Okay, moving on. Okay, so our project is diagnosis prediction from chat text. The company is K-Health. K-Health is a medical AI startup company. Their main product is K, which is an application that is an AI personal health assistant. It allows users to put in their symptoms. It gives them insight about similar users with similar symptoms. It also allows them to chat with a doctor and gets diagnosed and treated. We just want to mention all chat has been obfuscated to remove PII. And our mentors were Etam Benger from Data and Etam from K-Health. Okay, so what is our business goal? As we saw, the flow of the application is there is a symptoms collector, which is automated, followed by a chat with a doctor. The chat with a doctor is obviously the more expensive resource. And the idea is how can we save doctor time? So what we did and what the idea here is to analyze history of chats using a model that predicts the diagnoses, and then convert the results into insight of which symptoms and questions can be moved back into the symptoms collector, basically making it better and saving doctor time. Okay, so how does our data look like? We got chats, conversations between doctor and patient. Due to confidentiality, I won't show you a real chat, I'm going to show you a fake one. So this is an example. Doctor says, hi, I am doctor, fake name, how can I help you? And patient says, lately I smell like an onion when I speak, I need to consume a lot of mint. Doctor, have you been eating onions? Yes. Hey doctor, it sounds like you have hemorrhoids. So we get also labels, so which is the final diagnosis for the chat, in this case hemorrhoids. So where do the labels come from? There's a standard called International Classification of Diseases, ICD-10. 10 stands for the 10th version. And ICD-10 is very complex. It has 70,000 codes. It has 7 levels of hierarchy. For simplicity, let's imagine this is the tree. This is a small sample of a tree with just 4 levels, and we can see one branch with respiratory diseases and the second with mental disorders. For our first model, we're going to use what we call flat labels. The idea is we're going to cut the tree and choose a level, and we're going to predict that level. We're going to ignore the hierarchy, so we don't care what are the like above or below that level of the tree. That is our sort of final flat labels. And this is a little oversimplified. Okay, so the data. It's chat data. Most NLP libraries are trained on well-structured text, and this is like not the case here, so that imposed a little more complication to our project. And even though the data is challenging, why do we want to use it? So chat data compared to structured data is way more informative because it's an open, free conversation. However, it's also noisy, similar like the internet. There's a lot of useful information, but you need to clear out the noise. And the challenge here is how do you retain the meaningful information while removing the noise? And we show you how to reduce the data by 90%. First thing we did, EDA, we found repetitive text patterns that doctors use. They come in different variation. They're mostly noise for us because they come past the diagnoses. And they talk about prescription and medication, so we truncated those. That reduced the data by more than a factor of 2. But that didn't address our main challenge, which was target leakage. So as we said, we are trying to predict the diagnoses. However, if you remember the fake chat, the doctor actually gives the diagnosis in the chat. So what we're trying to predict is part of our data, which means we have target leakage, we need to remove it. Target leakage is an unsupervised task. No one gave us labeled data saying this is leakage, this is not leakage, so we needed to tackle 2 issues. First is uncover where the leakage is hiding, and the second is how do we know we're making progress, how do we know we're successful? So onion is a repetitive motive in the picture. So when we think about it, where is the leakage hiding? It makes sense the leakage is hiding in the doctor text because the doctor is the one giving the diagnosis. Conditions are the obvious leakage, but conditions, medication, referrals are all highly correlated and are leakage, so needs to be removed. But what happens if the doctor says to the patient, you have a UTI, and the patient asks, well, how do you treat a UTI? In that case, the leakage, the patient echoes the leakage from the patient and needs to be removed. So that's another decision we make. And also we found implicit leakage. Doctor says you must go see a dentist, you must drink water, stay quarantined, etc. So leakage is like removing the leakage is like peeling an onion. You peel one layer of leakage, you find another one, and you cry in the process. How do we measure the effect of leakage? So first of all, we thought we can see what is the model actually learning. So we ran the data through a TF-IDF vectorizer with logistic regression. Logistic regression is great in the sense that it gives you feature importance per diagnosis. And we saw what is the model actually learning. And what we found was awful. So basically what the model is picking up is all the leakage. So for asthma, first thing it catches is the asthma followed by a list of medication. So we can clearly see the leakage in the feature importance. The second is we can split the data and evaluate how the model is doing on data on doctors separately, patients separately, and all data. When we did this, we also saw a clear image of leakage where the model is performing the same way on doctor data and all data, which means the model is giving a prediction for the patient without considering the patient data. We can throw away the patient data and the performance won't change at all. So that's a clear indication of leakage. We expect to see a reduction in the doctor's performance the more we remove more leakage. So we started with a list of conditions, parsed out ICD-10, used the K resource, and similar words, using word-to-vec and word embeddings. Why similar words? Conditions can be referred to in many different names: flu, influenza, flu with an E apparently. There are common acronyms doctors tend to use, which we weren't even aware of, but we found through the similar words. Also just to get more coverage of conditions to remove. Someone who hasn't watched the presentation and wants to guess what is the most similar words to LOL?
Understand.
What? Okay, so I'll tell you. It's haha, followed by ha ha ha. So it's pretty good, it works pretty well. Next we went to find medications. And we decided to use vector algebra. So we all know the famous man to woman, king to queen, so we decided to adapt that to our use case and say, okay, let's take a few known conditions and medications and run all the different conditions and see what we get. And this actually produced pretty good results. Now it's played, so we can see that UTI to macrobid is like pink eye to eye drops, and if we put flu there, we will get Tamiflu. You can stop that video. Oh, okay, cool. So it worked pretty well. We ended up not using it because we got a medication database from K, but it was a fun experiment. We also use, of course, similar words because the medications are not easy to spell. So what's the catch? We used similar words. Similar words is an unsupervised task, and we wanted to remove as much leakage as we could. However, we found we were getting symptoms into our leakage lists because of the similar words. So we decided we need to protect the symptoms. How do we find symptoms though? So again, vector algebra to the rescue. Finding conditions to symptoms relationship tend to repeat across conditions. So another small demonstration. Oh, sorry. Okay. Yeah, so we can see here like UTI to burning is like flu to scratchy throat and runny nose and sneezing. There's a lot of symptoms for flu. And to asthma like wheezing and shortness of breath. So it worked pretty well. But still, so we were seeing improvement, but however, the doctor features, when we looked at them, were still pretty meaningful. Our main goal was to find good features that can be incorporated back to the health dialogue, and these didn't seem so good. So we were sort of hit a glass ceiling, and then we had an epiphany. We said, what do we really need from the doctor text? And we realized what we need are requests for information, meaning questions. What is the doctor asking the patient? What information? So we built a rule-based heuristics for extracting questions and requests from the doctor's text and removed anything else. So that was a big leap for us in the target leakage process. And after that, we could see that the model went from 0.69 to 0.34, which is a factor of 2 for the doctor. And the features are now way cleaner and more meaningful. So Now that we have our leakage removed, we could move on to more standard NLP processing, which we don't have time to go into. And then said, okay, let's use the model, logistic regression, and DF-IDF vectorizer. And then decided, well, before we do that, we actually want to do like a little finer replacing n-grams because we don't want to use the vectorizers because we don't want to cross sentences or speakers. Another thing we decided to do in order to get more meaningful features, to be able to interpret the features better later, is we prefix the doctor and the patient words in n-grams with doctor or patient. So that will allow us later to interpret the features more easily. It went to the TF-IDF vectorizer and a logistic regression model. Looking at the results, Okay, looking at the results, we got a weighted F1 score of around 0.5, which is, okay, that's going to be our baseline. But more importantly, we wanted to look at feature importance. What is the model actually learning? And this is an example of disorders of urinary system, and you can see doctor features in yellow, patient features in blue, and you can see we get pretty good features, like urgency, frequency, burn urination is a self-explanatory feature, and it's clear what the doctor is asking. However, not all features were clear. So when we looked at strap, we actually saw really good features with a weird in the middle, which seemed like really weird. So we built heuristics for, we built a mechanism for extracting back the questions based on the features. So when we did this and ran it on we actually found that this is a request for sending a picture saying So pretty awesome. And then we also wanted to interpret the patient features. So, because if the patient, we have ibuprofen, what do we do with that? It's not very meaningful. So what we did is we extracted the last question that was asked before the feature appeared in an answer. In this case, we can see ibuprofen was a response to what have you been taking so far, like over-the-counter medication. Okay, so the model has been doing pretty well, so why is the score not great? And like, let's look at where it's making mistakes. When we looked at the most common misclassification, we found that the model, the mistake it was making were pretty reasonable. It was like confusing cystitis with like disorders of urinary system, which are pretty close conditions. So, and all of the list of conditions it was confusing were very close, were very similar. So how do we capture that in metrics? Remember we talked about the flat labels? Before we were ignoring all the hierarchy in the labels. Now we're going to take advantage of the hierarchical labels, and for each label we're going to take the full hierarchy, so which family it belongs to all the way up to the top. So the reason behind it is like a flat model, an error is an error. It doesn't matter if I confuse anxiety with depression or anxiety with strep. From a flat model perspective, this is an error and that's it. But if we use hierarchical metrics, then anxiety and depression, which are closer together and are more similar, will be penalized less than two conditions that are very far apart in the hierarchy. So how do we do that? I'm not going to get into the formula of hierarchical metrics. We basically use a sort of variation of a hierarchical F1 score. But the idea is it takes into account all the levels of the hierarchy. In this case, confusing panic disorder with anxiety. The model was correct on 3 levels out of 4, so it will get a pretty good score. Unlike if I confused a cystitis with general anxiety disorder, which was wrong on all 4 levels. So you can see the difference. So when we evaluated the flat model with the hierarchical metrics, we actually got a better score. So we got a 0.67, which is an improvement with comparison to our 0.5. So if our hierarchical metrics are good, why not try hierarchical model, which is even more, should even leverage more the hierarchy in the labels. So credit here goes to Maor Gidron and Moshe Shalom. They were a parallel team working on K-Health, another K-Health project. They were working on structured data, and they built an hierarchical model based on LCPN, Local Classifier for Parent Node, which I don't have time to get into. But basically, this is like a set of classifiers where the data goes down the hierarchy based on predictions from previous level. In that sense, I just want to say that Moshe and Maor also created a sophisticated version of the flat labels which we were using. So before, when I said flat labels, it wasn't really flat, it was more an advanced version of the flat labels. So they did amazing work, and thank you. So we ran our data through took our model and data and ran it through their hierarchical model architecture. And surprisingly, we actually didn't get better results. We got pretty similar results. When we looked at why is that, we found that the hierarchy is a bit problematic. There are ambiguous categories, and what happens in a hierarchical model is that errors propagate down. If you make an error on one of the higher levels, the error will propagate all the way down, and you will get penalized for that. So we found like sort of ambiguous categories like unspecified STD versus other STD, and sort of different conditions that are very close but appear in very different branches. So the hierarchy can work for you when it's good, but it's problematic. It can cause some issues. So the score is not only the thing that matters to us, because we care more about explainability. So what the hierarchical model did give us is the ability to look at feature importance per level. So now we can see, like in the hierarchy, the diagnoses become more and more specific the more you go down the tree. So we expected the features to also become more specific. And this is an example for that. So for the first level, just distinguishing this is a mental disorder diagnosis, there's a depression multiple choice question. This is a token we use to replace multiple choice questions. We can see that, which is very general. On the second level, which is mood disorders, we actually see the doctor asking about mood swings. And on the third level, which is bipolar, we actually see even more specific questions about recent change, skin, hair, weight. So that's pretty nice. For summarize, so we were able to clean the chat data, got it down, removed noise and leakage, and reduced 92% of it. Went from 500 to 40 words on average per chat. And what we built is basically a model explainability system where K now can put in a condition and get out what were the most important features for that condition, doctor and patient separately. They can get what were the exact question and context for that. They also get all the doctor's questions related to that diagnosis. So that should allow them to make the symptoms collector better, see what can be moved into the structured health dialogue. Future work, there's so much potential to this project, so many things we can do. I won't get into it because I'm guessing over time anyway. And that's it. Thank you.